Hello everyone. Hope you all are in good health. It's difficult, replicating the experience of the classroom, but still we are trying our best to help you people out. As far as the classes are concerned, I'll suggest if you get stuck up anywhere, you're not able to understand a particular concept, at best what you can do right now is replay the video, hear it once again, and I'm pretty sure that you'll be able to do good. As far as the numericals are concerned, I'll suggest pause the video, take down the questions, attempt yourself first, and then you can always look at the solution. So, in the class, we started with the concept of torque. We had a few classes, and I'm hopeful that the basics were clear, but still, once again, we'll recall the things and then we'll proceed towards the questions. So we talked about that how torque, or the turning effect of force, is defined as the product of force and perpendicular distance between the line of action of force and the axis of rotation, right? So the expression tells us that torque depends on both the things. How much force are we applying in order to turn something, example a door, and where are we applying that force, the point of application of force, perpendicular distance. For example, if we take the case of a door, we apply the force at the handle, and the axis of rotation is the imaginary line passing through the hinges. So that is the axis of rotation, and this imaginary line running through my hand is the action of force. So the perpendicular distance is this thing, right? So we can see from here that in order to get maximum turning effect, maximum torque, we have two ways. Either we increase our force, and second, increase d, that is the perpendicular distance. Now in most of the cases, whether it's a door, whether it's turning the steering wheel of a car, of a bus, or whether it's the hand floor grinder, in all these cases nobody likes to use more force. Given an option, we all would like to open this door with a lesser amount of force, right? So the concept tells me that it doesn't really matter how much force we are applying, the door needs a particular amount of torque to get opened. I'll elaborate on that. Suppose for opening of our door, the torque required is 20 Newton meter. Unit you can check from here, force in Newton, distance in meter. So this door requires 20 Newton meter torque to get opened. Now one way of obtaining that 20 Newton meter torque is I apply a force of 20 Newton and the perpendicular distance between the axis of rotation and the handle, that means the line of action of force, is 1 meter. Okay, and I'm applying 20 Newton, remember? So that way also I'll be able to generate 20 Newton meter torque. Another option is I apply 5 Newton force. So the perpendicular distance needs to be 4 meters. So 5 into 4 will again give me 20. The door will anyway open. I can apply a force of 1 Newton also, but for that the perpendicular distance needs to be 20 meters. So you see, the door, in order to get opened, it requires its 20 Newton meter torque. Whether you give it by applying 20 Newton force, 5 Newton force, 1 Newton force. So my point was that given an option, all of us would like to use lesser force. So for that, you need to increase D, perpendicular distance. So with this example, I'm sure it is clear that torque depends not on one, but on both the factors, right? Now, coming on to the next point, many a times I find that there's some confusion regarding torque and force. See, very clearly you have to understand force is a concept of translational or linear motion. Remember in class 9, we were taught that force produces acceleration. If a body is at rest and you apply an unbalanced force, the body comes in motion. That means it gets accelerated. If a body was in motion and you apply an unbalanced force, it might come to rest. Again, deceleration, negative acceleration. So force produces acceleration. Torque is a rotational concept. Whenever there is rotational motion happening, we use this term torque. For example, if I discuss the case of a fan moving at a particular speed, and then I ask you, is this fan accelerating? Come on, what's your answer? Is it accelerating? If in case you said no, then please listen carefully. Because the direction of motion is continuously changing, therefore its velocity is changing. And we know that acceleration is rate of change of velocity. So if the velocity is continuously changing, that means the fan is accelerating. You might feel that it's running at a particular speed, at a constant speed, I'm not touching the regulator. But because of the change in direction, there's a change in velocity and hence acceleration. So if I ask you, what is causing acceleration? Our previous concepts tell us force. But let me tell you, because this was a case of rotational motion, we should use the term torque. It's the torque produced by the motor inside this fan which is causing the acceleration. So remember this difference very clearly. Force is a concept of translational or linear motion, whereas torque is a concept of rotational motion. Okay? Okay. So after knowing the basics, let's go to the second point, that is equilibrium. The definition says, when a number of forces acting on a body produces no change in its state of rest or of motion, then the body is said to be in equilibrium. Remember, when a number of forces, two or more than two forces, are acting. Example. Suppose this body is already at rest, and now somebody applies a force of 5 Newton towards left, and some other person applies a force of 5 Newton towards right. Now, do you think this object will come in motion because of that? No. A number of forces are acting on this body, but this body was at rest and still is at rest. So this body will be in equilibrium. And because it was at rest, so we call it static equilibrium. Okay? Another example. This object is kept on a table. So if we analyze, one force is the weight of this object, which is acting vertically downwards. And since I can see that it is not going downwards, that means there has to be some other force in the vertically upward direction which is balancing its weight, and it has to be nothing but the normal reaction from the table, or in this case from my hand. So the normal reaction is balancing the weight. A number of forces are acting on this body, and this object was at rest and still is at rest. So this is static equilibrium. Fine. Similarly, another example, suppose a ball is rolling on a frictionless surface. Remember, frictionless. So what are the forces acting on this ball? No friction. What are the forces? The weight of the ball will anyway act. The reaction from the ground will anyway act. So a number of forces are acting. But because there is no friction, so we know that this ball is not going to stop. It is going to move with uniform velocity. So a number of forces are acting on this ball, its weight is acting, the normal reaction from the ground is acting, but still it is able to maintain its uniform motion. Dynamic equilibrium. Another case. The case of a falling raindrop. So a raindrop has some weight, and because it's falling through air, it is experiencing the upthrust due to air. And there's one more force which in class 10 we don't know much about in great detail, but still that one is known as viscous drag. It's like friction in solids. Okay? So because it is coming through the air layers, so those air layers, when they have relative motion between them, they exert a similar force like friction, which we call as viscous drag. So in short, the raindrop experiences weight, upthrust and viscous drag. A number of forces are acting on this raindrop. But we know that a raindrop comes down with a uniform velocity, with a constant velocity, which is known as terminal velocity. So this is an example of dynamic equilibrium. So when a number of forces, two or more than two forces acting on a body produces no change in its state of rest or of uniform motion, then the body is said to be in equilibrium. Right? Next thing is, what are the conditions for a body to be in equilibrium? How will we come to know that whether a certain body is going to be in equilibrium or not? Two very important points. First, the sum of all the forces acting on the body should be zero. In simple language, net force on the body should be zero. And the second condition is the sum of all the torques acting on the body should be zero. In simple language, net torque is zero. Let us understand it with an example. Suppose this is a rod fixed about this point, fulcrum, pivot, knife edge, all different names for the same thing. It's pivoted here, and suppose a 20 Newton force is acting from here. A 5 Newton force is acting from this point. A 15 Newton force in the upward direction. And also a 10 Newton force in the upward direction. So we need to know whether this rod is going to be balanced or not. That means in equilibrium or not. Let us use the first condition. Whether the sum of all the forces acting on this rod comes out to be zero or not. We can see the net downward force acting is 25 Newton and the net upward force acting is also 25. So definitely the net force is zero. The sum of all the forces. Suppose downward force we are considering positive. So the upward force would be with a negative sign. So the sum of all the forces, downward plus upward, you can see is coming out to be zero. But this does not alone guarantee whether this rod is going to be in equilibrium or not. Remember, we talked about that force being a concept of translational or linear motion. So the first condition only tells me that this rod is going to be in translational equilibrium. That means the rod is neither going to go down or up, but it can still tilt. Okay? So, in order to check whether this rod will tilt or not, we need to talk about the second condition, which is related to the torque. Let's use the same example. So let's say the axis of rotation will always pass through the fulcrum. So this force of 20 Newton about the fulcrum you can see is giving me anti-clockwise torque. This force of 5 Newton about the fulcrum is giving me clockwise torque. This force of 15 Newton about the fulcrum is giving me clockwise torque. This 10 Newton about the fulcrum is giving me anti-clockwise torque. So which two forces are giving me anti-clockwise? 20 and 10. Okay? So suppose this distance is 4 meters. And this distance, suppose, is 1 meter. So anti-clockwise moment or torque will be, remember, torque was F into D. So force 20 into its perpendicular distance from the fulcrum, 4. That is 80. Plus this one was also giving anti-clockwise. So force is 10 and its perpendicular distance is 1. So 80 plus 10, that is 90 Newton meter, is my anti-clockwise torque. Clockwise moment. Suppose this distance here is 3 meters. So force is 15 and distance is 3. Plus this one was also giving me clockwise. So suppose this distance till here is 9 meters. Just an example. So force 5 into distance 9. So 45 plus 45, 90. Net torque is coming out to be 0. Anti-clockwise moment is coming equal to clockwise moment. So neither the rod is going to tilt this way or this way. So for the rod to be both in translational as well as rotational equilibrium, you see, we need to satisfy both the conditions. The sum of all the forces acting should be 0 and the sum of all the torques acting should also be 0. I hope you have understood the basics. Thank you. Hi everyone. So we'll continue from where we left in the previous class. Principle of moments. A very important concept in this topic. You remember, torque is also known as moment of force. So this principle talks about the application part of torque only. This was our pivot fulcrum. The axis of rotation always passes from the fulcrum. There can be a number of forces acting. Suppose we take these many forces. Okay. Now, the principle of moment says in equilibrium, the sum of anti-clockwise moment is equal to the sum of clockwise moment. In equilibrium, the sum of anti-clockwise moment. So, let's see whether this rod is in equilibrium or not. So, this force about the fulcrum is producing anti-clockwise moment, and this force of 20 Newton is also giving me an anti-clockwise sense, whereas 15 and 5 both are giving me clockwise torque. So let me find out how much is the anti-clockwise moment. Force into perpendicular distance. This, let's say, is the midpoint. So 50 plus force 20 into the distance from the fulcrum. You can see it's 40. So this is 500 plus 800, that is 1300 Newton meter. For clockwise moment, 15 into the distance is 10 plus 5 into this distance is 50. This comes out to be 150 plus 250, that is only 400 Newton meter. So you can see in this particular example that anti-clockwise torque or moment is not getting balanced by clockwise moment. So this rod is definitely not in equilibrium. Fine. Let's take down a few more examples. Okay, so the question tells me that 40 gram force weight is placed at this mark. How can we balance this by placing 80 gram force weight? Let's apply the principle of moments. We need to balance this. So, we can see that this force produces an anti-clockwise torque. Force into distance from the fulcrum, let's call it 0. So the distance is 40. Anti-clockwise moment is coming out to be 1600. Be careful of the unit. This is not in Newton now. This is in gram force. We'll put it in gram force, and these values are given in centimeters. So no need to change unless they ask you the answer in SI unit. You can always leave your answer like this. So anti-clockwise moment is 1600 gram force centimeter. We need to balance it with a weight of 80 gram force, with a force of 80 gram force. So we already know the force. We don't know its location. We don't know the distance from the fulcrum. So let's call it X. Now, according to principle of moments, if this rod needs to be in equilibrium, its anti-clockwise moment should be equal to its clockwise moment. So we can see that X comes out to be 20 centimeter, but obviously you want it clockwise, so it needs to be on this side. So from here 20 centimeter, if we put our 80 gram force, you can see 1600 anti-clockwise and 1600 clockwise moments, they will get balanced. So this is a simple idea of principle of moments. Okay. One more example. Okay. So the first part of the question says whether this ruler is in equilibrium or not. So let's see how much is the anti-clockwise moment. Force 40 into perpendicular distance, remember always taken from the fulcrum. So 50 minus 10, so this is 40. So anti-clockwise is 1600 gram per centimeter. And clockwise moment, force is 20. And its distance from the fulcrum, 90 minus 50 is 40. So this is only 800. So as we can see, anti-clock and clockwise moments are not equal. So the answer for the first part is this ruler is not in equilibrium. Which way will it bend or turn? Obviously, because anti-clockwise moment is bigger, so the rod is going to tilt or bend towards the anti-clockwise side, right? The second part says, how can we balance this? By placing an additional weight of 40 gram force. Now from the working, it's very clear that with that 40 gram force, you want a clockwise torque because anti-clockwise is already greater. So for clockwise torque, we need to put that 40 gram force somewhere towards the right side, right? For the working, we wanted this ruler to be in equilibrium. So anti-clockwise moment should be equal to clockwise. Plus, we have got now an additional 40 gram force. But where do we keep it? Let's say X from the fulcrum. Why are we putting this equal to sign? Because we want this ruler to be in equilibrium. Anti-clockwise is equal to total clockwise. So let's solve it. X equal to 20 centimeter. Now, don't put it here. 20 centimeter from the fulcrum on the clockwise side. So from the fulcrum, 20 centimeter on the clockwise side, we need to put our 40 gram force. So our final answer is 40 gram force should be placed at 70 centimeters.